Testing. Oh, it's okay. Yeah.
So, very good afternoon, everyone. It gives me great pleasure to introduce Professor. Okay, a very good afternoon to everyone again. It gives me great pleasure to introduce Professor Ram Murty, who is an A.V. Douglas Distinguished Professor, Queen's Research Chair, Fellow of Royal Society of Canada. He's also a Professor of Philosophy, but more importantly, he has been a long-time friend of IMSC, and he has trained many graduate students and future generation mathematicians, actually 3-generation mathematicians in his lifetime. So it's an honor for me to introduce him, and he is going to tell us about Ramanujan and his legacy.
Okay. Thank you very much. I hope this microphone is working, or is this on? It is on? Okay. Oh, it's on. Okay. Okay, everybody can hear me? Good to see everybody. Good to see all of us together. And as Anup has said, I have a long association with this institution, and I'm proud of that association. I feel very much that I'm a member of a very large family every time I come to India, and if the sense of belonging defines one's identity, it seems that this is where I belong. So today I want to discuss with you about Ramanujan and his legacy, and it is meant as a general audience talk, so try to keep the math at a kind of a less technical level. The story of Ramanujan is essentially a story of rags to mathematical riches story. And in 1999, Robert Kanigel wrote this book called The Man Who Knew Infinity. And Kanigel, not being a mathematician, was unable to determine the impact of Ramanujan's work. Although the book is nice from a general public perspective, from a mathematical perspective, it was not a definitive work. There are 4 themes that are not really discussed well in the book, and these have to do with the contributions of Ramanujan, with the contributions of, oops, I think there's some feedback, the contributions of Ramanujan with respect to 4 themes of mathematics. First is the normal order method, the second is the partition function, and the circle method. Third is, of course, his impact on the development of the theory of modular forms. And finally, the 4th is the development of the theory of mock modular forms, which is still ongoing. So the story of Ramanujan is very inspiring from very many angles. Firstly, his humble beginnings. He was born in 1887, as all of you know, on December 22nd in this town, Erode, India. To a large extent, he was self-taught, became a universal genius with his fundamental contributions to number theory. And this talk is a panoramic view of how this transformation came about. So here's Ramanujan's house in Kumbakonam. His childhood was filled with intellectual adventures, the first being this book by Loney called Plane Trigonometry. He borrowed it from a friend at the age of 12 and completely mastered its contents. And the book goes far beyond standard trigonometry and also treats rudiments of calculus. So by the age of 12, here we have Ramanujan learning calculus. But the book that transformed him is this book called Course Synopsis of Pure Mathematics, used by many students in Cambridge University to review material for their PhD examinations. So Ramanujan borrowed this book from the local library and delighted in proving the results that were contained. The book contains no proofs. It just is a compendium of facts. And so he took each fact as a problem to be solved and re-derived everything on his own. So, but being poor to own paper or buy paper, he had a slate, and he would write on the slate, work out the examples, and rub off the the material from on it with using his elbow. And many people talked about Ramanujan's bruised elbow, and we now know how he got that. His college days, he went to this government college in Kumbakonam at the age of 15, and unfortunately failed his exams because he spent too much time in mathematics and neglected the other subjects. And then he later moved to Pachiyappa's College in Madras, now Chennai, and unfortunately same thing happened. He failed due to his neglect of his non-mathematical subjects. So all this means that failure is no indication of inability. Now, so having failed everything, he had to get a job, so he got a job as a clerk in the Port Trust office. And he also tutored many students in mathematics and somehow eked out an existence. But he found leisure to do mathematics and jotted down his results in his famous notebooks. These famous notebooks were written more or less at that time. And you know, to this day, I keep saying everyone should have these notebooks. I mean, certainly you should have Ramanujan's notebook, but you should have your own notebooks where you sit down and study in your own way. You have to personalize knowledge in order to really know it. All right. So these are the famous Ramanujan notebooks. I believe they're still here in the Ramanujan library, Ramanujan Museum. Now, many people are of the impression that it was G.H. Hardy who helped Ramanujan reach international fame and so on and so forth. That could be to some extent, but many don't know that there are two Indian mathematicians who were very helpful, Ramachandra Rao and Seshu-Narayan Iyer. In the Port Trust office. They were both instrumental in helping Ramanujan. They discussed many mathematical ideas with him. And I believe it was Iyer who suggested Ramanujan that he write to G.H. Hardy. It may have been Iyer who also edited Ramanujan's letter for English grammar and spelling. So Ramanujan's first letter, famous letter to G.H. Hardy, it seems Ramanujan wrote to 3 other mathematicians before he wrote to G.H. Hardy, and two of them never replied. One of them said he better go back to school, and it was only G.H. Hardy who actually gave him a serious response. So the letter, after a brief introductory paragraph saying that he's a clerk in the Port Trust office, etc., which I think all of you know, goes on and lists formulas for the next 10 pages. So there's G.H. Hardy. It's hard to find a picture of G.H. Hardy without a cigarette or a pipe. So anyway, but nowadays we can perhaps Photoshop these pictures. Okay, so for the next 10 pages, you have these theorems page after page. So here's a sample page. Is that visible? I kind of see it? Yeah. So if you, when you look at something like this, page after page, these formulas without any explanation, Hardy thought, is this the work of a genius or is it the work of a crank? And there were 120 theorems stated in this letter. Now before I go on, I just want to highlight one particular entry that will play an important role in my discussion of Ramanujan's contributions to mathematics. This particular entry says that if you essentially take the reciprocal of a certain theta function, you can calculate the nth coefficient of the power series exactly, more or less, as a nearest integer to that hyperbolic sine and hyperbolic cosine term that's there. So I just want to put that in your mind as I proceed with the lecture. So here are more extracts from the lecture. These are all printed. Of course, this is not the handwritten version. Was typeset in the collected works of Ramanujan, and I just took these pages out of that other work. So here's one more. Page after page of this stuff. So now this entry, 27th February 1913 entry is interesting. So here's more formulas that keep on appearing, which are fascinating in their own right. And why is e to the pi square root 58 very close to a whole number? Well, there's a deep reason for that. Ramanujan seems to have stumbled on this thing. But let me highlight this 27th February 1913 entry. He says the number of primes up to x is given by this integral 2 to x dx log x minus 1/2 dx over log x up to square root x minus 1/3. It's an it's a kind of a oscillating series, and the term is essentially the Mobius function. And this explicit formula for the number of primes was given by Riemann in 1859. And Ramanujan couldn't have possibly read Riemann's paper because it was written in German. And so he has this tendency of re-deriving everything by himself. And I think that's probably the best way to learn anything. You have to re-derive things for yourself. You have to do what Ramanujan did. Now, Hardy's reaction is interesting. He lost sleep that night, and he invited his colleague Littlewood to come over and have a look at Ramanujan's letter. So well past midnight, about 3 in the morning, they concluded this was the work of a genius. So he says, a single look at them is enough to show that they could only be written down by a mathematician of the highest class, because they must be true, because if they were not true, no one has the imagination to invent them. This is the very nice quotation. So Ramanujan sails for England. Hardy makes the arrangements with one of the mathematicians who was in charge of the University of Madras. From 1914 to 1917, Hardy and Ramanujan had a fruitful collaboration. During that time, Ramanujan wrote over 30 papers, 7 of them jointly with Hardy. So just imagine the rate of productivity. 30 papers in 3 years, 10 papers a year. We have trouble writing 3 or 2 or 3 papers a year. So it's a very prolific time period for him. And we'll highlight 3 of these papers since they shaped the course of 20th century mathematics. So what are these 3 fundamental papers? First is called the normal order method, written in 1917. The second, circle method, asymptotic formulae in combinatorial analysis, 1918. And then the famous paper, Ramanujan conjectures on tau n, coming from this paper called Certain Arithmetic Functions, written in 1916. Now, what is the normal order method? Let me just try to explain this in lay terms as much as possible. If you let omega of n be the number of distinct prime divisors of n, then how does omega n behave? It behaves very erratically. Omega n is 1 if and only if n is a prime power. And the question was, is there regularity in the behavior of omega n? And Hardy and Ramanujan noticed that with probability 1, omega n is usually hovering around log n. So this is an interesting theorem that they seem to have shown. They didn't state it in probabilistic terms. They stated the normal order method thing. And so a more precise version is that the deviation between omega n and log n isn't very big. It's about square root log n. And so in other words, with probability 1, usually omega of n hovers around log n with some sort of deviation of square root log n. Paper was innovative for its use of some elementary sieve techniques. But it was Erdős and Katz who generalized this theorem and noticed that there's actually a theorem in probability theory that this thing is about. Namely, they showed that if you take omega of n, subtract the mean value, which was log n, divide by the standard deviation, which is root log n, this function has the normal distribution. So norm 5ab is the normal density function. So this theorem was proved in the 1940s. It led to the creation of a new branch of mathematics called probabilistic number theory, and inspired some new methods in sieve theory as well. So this is Paul Erdős and Mark Katz. There's a nice story that goes with this thing, but I don't have time to talk about it. But it's interesting how these developments came about. Now, the next theme, paper that Ramanujan and Hardy wrote has to do with what's called the partition function, a famous function both in mathematics, representation theory, and physics. So this is basically the number of ways of partitioning a natural number. So 4 can be partitioned, for example, in 5 ways, as simply 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, 2 plus 2, 1 plus 3, or simply 4. The order of the summands is irrelevant. So P of 4 is 5. Question is there any methodology? Can we explore how this function grows? And so the first observation to be made is that each partition of n can be factored as K1 plus 2K2 plus 3K3, etc. Sorry about that thing. I think it has to do with formatting. It's easy to see that P of n has a generating function given by summation n going from 0 to infinity, k equals 1 to infinity, 1 over 1 minus x to the k. So using that unique factorization of the partition, you have a generating function. This was discovered by Euler. So Hardy and Ramanujan discovered, using the circle method, an asymptotic formula, namely that the partition function grows exponentially, e to the pi square root 2n over 3 divided by 4 over root 3. This is the famous Hardy-Ramanujan formula for P of n. Now in 1937, almost 20 years after this paper was written, Hans Rademacher came up with an explicit formula, not an asymptotic formula, explicit. And this formula reads something like this: P of n is equal to 1 over pi square root 2, summation k going from 1 to infinity, root k, ak of n, I'll tell you what ak of n is in a second, times this d by dn, this hyperbolic sign, over root n. Because ak of n is certain exponential sum defined by what are called Dedekind sums. So we'll not worry too much about these sums. They are interesting in their own right. This is not the time for discussion of those things, but we will highlight the important term in this expression, which is d by dn of a hyperbolic sine function. Now if you remember the first letter of Ramanujan to G.H. Hardy, he has a hyperbolic sine term function saying it's the nearest integer, as if he had the intuition that there's an explicit formula for those coefficients. And this exactly is the matter at hand. In many ways, experts such as Selberg would say, look at this and say, why didn't they get the Rademacher formula? Because everything was in place for that. So, as I said, to point out this thing here, we have this expression that I mentioned, and that's relates. So Selberg, Atli Selberg says something very interesting. In fact, Atli Selberg made these comments at the, I think it was the 100th anniversary of Ramanujan's birth in 1987 at the Tata Institute. So he said, in the summer of 1937, I had actually myself been studying number 36 in the collected papers of Ramanujan and had arrived at Rademacher's formula. So what we can infer from this is Selberg independently derived Rademacher's formula for himself. It always seems strange to me that Hardy and Ramanujan did not end up with this formula, and I believe firmly that the responsibility for this rests with Hardy. So this guy's going to be hard on Hardy. This is a very balanced, accurate, fair assessment of what happened. Hardy, being an analyst, was looking at things asymptotically. Ramanujan, being a number theorist, was always looking at things arithmetically. So when you go into asymptotics, you lose the integrality and the divisibility properties and so on and so forth. So in January 2011, an interesting thing happened. Brunier and Ono discovered an exact formula using Ramanujan's theory of Mach modular forms, and showed that P of n is a finite sum of special values of weak Moss forms evaluated at CM points in the upper half plane and discovered 24n plus 1. Now let's not worry about what CM points are. Here's a picture of Brunier and Ono. Where are they? Brunier is there and Ono is there. And this is from a conference that I was at with them in 2003. Rather young picture of myself. The other people in the picture are Youngju Choi, Winfried Konen, the back, and Masabu Kaneko, who from Japan. So we all 6 of us were recruited at that time to give a short crash course on modular forms at that, and these two spoke about this work. So now recent developments, we used the formula, Michael Dewar, myself, in October 2011. Without using the circle method, we used that asymptotic, the algebraic formula of Ono and Brunier, and showed that you have a nice asymptotic expansion you can get without using the circle method. And so far we also have a new way, we meaning we as mathematicians have a new way, due to Baez Duarte in 1997, I think he's a Chilean mathematician. He managed to show using the central limit theorem that you can get the asymptotic formula for the partition function. Now this is something that I wanted to cover in my mini course in Prayagraj that I gave this last week on probability theory and number theory, and of course there was just too much material to cover, so had to confine myself to not dealing with this. But this is an interesting paper which is well worth reading in detail. And the paper is not long, it's only, I think, under 10 pages. So any aspiring young student here wants to study something related to Ramanujan, I would recommend that paper. Now the generating function of the partition function, as I mentioned in the earlier slide, is given by this formula. And the key observation is when you put x equals e to the 2 pi I z, the right-hand side becomes what's called the Dedekind eta function, which is a modular form of weight 1/2. And this means that there's some sort of modular relation, eta of a tau plus b over c tau plus d equals some epsilon factor, which I will talk about in a second, c tau plus d square root and eta of tau. This epsilon factor turns out to be a 24th root of unity. It's a complicated 24th root of unity. Involves those Dedekind sums that I had mentioned in the earlier slide. Very interesting thing. And what is interesting is if you take the 24th power of the eta function, that root of unity disappears, and you get this famous, the delta function of Ramanujan, which is a modular form of weight 12. So this is, these A, B, C, D have to be in SL2Z. Now, so Ramanujan's conjectures and the theory of modular forms. So far I mentioned to you, I was going to focus my attention on 3 themes: the normal order method, the circle method, and the theory of modular forms. So far I've discussed the 2, and now let me discuss the modular forms. This paper of Ramanujan, written in 1916, introduces the tau function in a substantial way to the world. And the conjectures that were made in that paper were discussed at length by Louis Mordell, developed later by Eric Hecke, and then Lehner, and then Atkin. So these are the 4 people who are credited in the 20th century as being the developers of the theory of modular forms. Hecke mainly, of course, and Atkin and Lehner, who completed the higher level theory. Eric Hecke did most of the level 1 case, and the higher level was done by Atkin and Lehner. Now, Ramanujan's delta function is, of course, this 24th power of the eta function, as I mentioned in the previous slide. And when you expand the power, the product q 1 minus q to the n to 24, you get these coefficients. And many, non-math people, perhaps, and non-number theoretic people ask me often about why the 24th power. And I told you one reason was to get rid of that 24th root of unity. Another thing is apparently it's connected, seems to me, somebody was saying that it's connected to string theory. I'm not an expert on this stuff, but perhaps there are experts in this room and they may be able to help us later on. But Ramanujan looked at this function and he was enamored by these coefficients of the power series. The power series begins q minus 24 q squared, 2 plus 252 q cubed, etc., etc. And as you can see, the numbers are getting bigger and bigger in absolute value. They may be changing sign, but they are certainly getting bigger and bigger in absolute value. We don't know how to prove that they actually grow, all of them grow uniformly large. We don't know how to do that. For example, there's a famous conjecture that tau of p never becomes 0. It's called Lamer's conjecture, and we don't know how to prove or disprove that. So we really don't know how if tau of n is uniformly going to infinity. We expect it does. We expect it does, but we don't know. But Ramanujan was more intrigued as a number theorist. He was more intrigued by the arithmetic properties of these things. And what he noticed was, if you take minus 24 and multiplied by 252, you get the 6,048. And so he started noticing patterns. I believe he calculated well into the hundreds. So he made these conjectures that Tau is a multiplicative function. Tau satisfies a second order recurrence relation for prime powers. And finally, the famous Ramanujan conjecture that tau of p is bounded by 2 times p to the 11 halves. These are called the Ramanujan conjectures. They were formulated by him in 1916. The first 2 conjectures were proved by Mordell immediately in the following year, 1917. And then Hecke's work can be seen as a generalization of those ideas to the full theory of modular forms. It's this last conjecture that was fascinating and perhaps difficult to knock. And in the 1950s, Mikio Sato noticed that this conjecture of Ramanujan had something to do with We's conjecture in algebraic geometry, and made that connection. And then in 1974, Deligne actually showed how resolution of the Weyl conjectures leads to a solution to the third conjecture of Ramanujan. So for this he was awarded the Fields Medal, but it is Pierre Deligne. Okay, so now Hardy makes some comments in his 1936 lectures on Ramanujan given at Harvard University. He makes some comments on the tau function that have become famous. So let me kind of remind you of what those statements are. He said, we may seem to be straying into the backwaters of mathematics, but the genesis of tau of n as a coefficient and so fundamental a function compels us to treat it with respect. So I underline the most important word in Hardy's statement is being may. We may seem. If you drop the word may, what does it become? Exactly the opposite. We seem to be straying into the back. But when you put the word may, we may seem means that we're not actually. You see the very subtle uses of the English language. But Andre Wey doesn't read that. In his 1972 writ lectures, Wey makes several pronouncements on 2 things. First, what analytic number theory is, and second, on G.H. Hardy. Both are erroneous. So Hardy's remarkable comment is, we seem to have drifted into one of the backwaters of mathematics. See this? So he says, Hardy's remarkable comment is, we seem to have drifted. He dropped the word may. We seem to have drifted into one of the backwaters of mathematics. And then he continued, to him, Ramanujan's third conjecture was just another inequality. He found it curious that anyone could get deeply interested in it. In fact, he becomes apologetic and explains that in spite of the apparent lack of interest in this problem, it might still have some features which made it not unworthy of Ramanujan's attention. So I just want to put these 2 side by side, and you be the judge. The judgment, on A, what Hardy said, and B, what analytic number theory is. These are both severe in my opinion. They are extreme and severe, and perhaps even unfair. Now, how did Wey come up with Wey conjectures? Well, here is an interesting and inspiring passage of Andre Wey, which is a credit to Wey himself. In 1947 in Chicago, I felt bored and depressed. And not knowing what to do, I started reading Gauss's 2 memoirs on biquadratic residues, which I've never read before. The first one deals with the number of solutions of ax to the 4 minus by to the 4 equals 1 over finite fields, and the second one with ax cubed minus by cubed equals 1. Then I noticed similar principles can be applied to all equations of the form ax to the m plus by to the n plus cz to the r plus ... equals 0, and that this implies the truth of the so-called Riemann hypothesis for diagonal equations. So what do we learn from here? We learn that if you're depressed and bored, you pick up Gauss and read the 2 memoirs, okay? Actually, the fact is, when you're depressed and bored, if you focus your mind on some creative work, you will come out of the depression. That's basically what this means, okay? So there is some wisdom in this passage. The key idea for this third conjecture has to do with Galois theory, Galois representation. So there's a representation of the absolute Galois group from Q into GL to ZL, such that the trace of the row of the Frobenius automorphism turns out to be tau of P. So let's not worry too much about what this means, but let's just extract from it that the tau function has a Galois connection. That's the key. And Galois theory is essentially arithmetic. Something fundamentally arithmetic is going on with Galois theory. So now I admit G.H. Hardy was no Galois theorist, but he didn't condemn the tau function. So Deligne proved Serre's conjecture and related this to Weil conjectures, thereby showing that Ramanujan's conjecture is a consequence of the Weil conjectures. Now, because of that elatic representation, we can now analyze when is this tau function divisible by some prime number L. And this is a question that intrigued Kumar and myself, and we tried to ask these questions in the 1980s, some time back. So some of that research work was done actually here at Math Science, so I thought it might be a good idea to report on this. Question is, how many prime divisors does tau of P have? Of course, we have to assume Lamar's conjecture that tau of P is never 0. Then the question that came up in our research, and we still don't know the answer to this question, is, are there infinitely many primes P such that P divides tau of P? I don't know how to answer this question. Maybe some youngsters in the room might want to think about this. It's an interesting question, or variations of this theme. So what we managed to do, as I said, work done 1984-85 here at IMSC, was to derive these Erdős-Katz type theorems for tau of P, namely that the number of prime factors of tau of P is very much like log P with a standard deviation of square root log P, and then you have a normal distribution law like this. So we worked that out. And unfortunately, we had to assume the generalized Riemann hypothesis. So I'm not going to discuss the generalized Riemann hypothesis here, but suffice it to say that my seminar lecture tomorrow will try to amplify some of these ideas, trying to see a general axiomatic framework in which all of these things become special cases. There's Kumar and myself. Okay, now after the conjecture of Ramanujan, the third conjecture is now known, that we now know tau of P is bounded by 2 P to the 11 halves. The question is, how are those values distributed? And as I mentioned to you, it was Mikio Sato who first noticed a algebraic geometric connection between the tau conjecture of Ramanujan and Weil conjectures. And then John Tate also noticed that there were some interesting things going on, but Sato was doing experimentation, so from numerical experimentation he was led to make some nice conjectures, and from theoretical considerations Tate was led to make some conjectures. And then Serre noticed that there was something larger going on, not necessarily restricted to elliptic curves as Sato and Tate were looking at, but something larger in the context of modular forms. And the conjecture is that tau of P divided by 2 P to the 11 halves is equidistributed in the interval -1 to 1 with respect to not the usual measure, the Lebesgue measure, but the Sato-Tate measure, 2 times square root of 1 minus x squared, dx over pi. So this is the famous Sato-Tate conjecture. Now, there's a version of the Sato-Tate conjecture called the vertical Sato-Tate conjecture, where we fix the prime and vary the modular form, and this is called the vertical conjecture. This was formulated by Serre also in 1997, and he proved that the Hecke normalized eigenvalues of weight k are equidistributed with a new measure, looks like a p-adic measure of sorts, mu p, p plus 1 over pi. 1 for each prime p, you have this measure. And so as you fix the prime and you vary the forms, the eigenvalues turn out to be equidistributed with respect to this measure. And now the general theme is whenever there's an equidistribution theorem, there's also an error term that has to be looked at. And this is the work, essentially joint work with Kaninika Sinha that I did about 2009, maybe 10, 12 years ago, where we showed that the error term can be explicitly written down as log p over log k. And this has now since been improved by Sarnak and his students just maybe a year ago, where the power of log p, log kn has been improved slightly. Okay. So what about the classical Sato-Tate conjecture? So in 2011, Barnett, Lamb, Ghirotty, Harris, and Taylor have proved this conjecture as a consequence of the Langlands program work that they were doing. Result applies to Fourier coefficients of Hecke eigenforms, uses representation theory, algebraic geometry, and number theory. So what is the point of all these statements? Just like you to understand that these rather simple looking innocent conjecture of Ramanujan on the tau function has spawned a lot of developments in the theory of modular forms, representation theory, Galois representations, algebraic geometry, and then led finally to this remarkable theorem. And Kumar and I were able to use this new development to finally settle an age-old problem about the maximal distribution, maximal order of tau of n. And it turns out that tau of n over n to the 11 halves has the same maximal order as the divisor function, which has, basically 2 to the log n over log n divisors, and that's the optimal that you can possibly get. So that number log 2 is the key that you can get using these results. Okay, this opens the door for a new branch of algebraic number theory, which is called the Chebotarev-Sato-Tate type theorems, where you can mix and match. And I think, Sudhir Pujari was talking about these mix and match kind of style theorems, Sato-Tate conjectures, and I think there's scope for many new theorems of this kind. So modifying the arguments of this BGHT paper, twisting by Art Nelson, one can deduce distribution laws with non-abelian conditions, like in the classical Chebotarev density theorem. So there's a lot of stuff that you can do in this context. There's more work to be done, and I think it's a nice program for youngsters in this room to embark on an intense study of this stuff and try to, because there's no one has really investigated this stuff. Okay, so now I have more or less given you a panoramic view of Ramanujan's work and his 3 papers and how they've impacted the development of number theory and mathematics in the 20th century. But then finally, the sad episode of Ramanujan illness has to be discussed. And in the spring of 1917, Ramanujan contracted tuberculosis and was admitted to the nursing home in Cambridge, England. Yes, under normal circumstances, anybody who becomes ill of TB, they sometimes might die, but they usually recover. But Ramanujan was also suffering from some form of depression because he did try to commit suicide in England. And the reason for that now we know is maybe due to the fact that he was not getting letters from home. The letters that he had been writing to his wife were never received by her. They were being intercepted by his own mother. So we now know that, and I think this is an important aspect of an individual as a human being. Perhaps the most important connection is the emotional connection, and the idea that you have to have a sense of belonging. So that could have contributed and aggravated Ramanujan's illness. He showed some improvement in the fall of 1918, was elected to the Royal Society at the time. I mean, there's a funny story of Hardy about the Royal Society, and when people tried to arrest Ramanujan for trying to commit suicide. I think there was an episode with the British police, but let me not go into the details of that. Early in 1919, he recovered enough to return to India, and shortly afterwards passed away on the 26th of April, 1920, at the young age of 32. And of course, the number 1729 is so famous, I can't resist telling that story about the taxi cab number 1729. When Ramanujan was ill in the sanatorium, Hardy comes and visits him in a taxi number 1729. On entering the room, he says, "I just came on a taxi number at 1729, which looks like a dull number. I hope it's not a bad omen." Now, here is an interesting phenomenon. So here we have G.H. Hardy, a representative of, in some sense, British society, British Empire, and so on and so forth. And you have Ramanujan, perhaps coming from India, superstitious, believing in omens. But the person who says it's a bad omen is not Ramanujan, it's Hardy. okay? I just want to point that out to you. And the retort that Ramanujan gives is, on the contrary, it's very interesting. It's the smallest number that can be written as a sum of two cubes in two different ways. I'm sorry about the formatting. I think when you change computers, these formatting things matter. And I tried to solve this, but I think some of the text is missing. So how do you write 1729 as a sum of two cubes? 1 cubed plus 12 cubed, and 9 cubed plus 10 cubed. So this is, and it's true, and I believe later on Hooley wrote a paper, the number of numbers that can be written as sum of two cubes in two different ways is extremely small. And Hardy actually has no excuse for not knowing 1729 or 1728 for that matter, because it appears in the denominator of the J function and various other, a delta function and so on and so forth. So he really should have known that. And of course the Mach theta functions and Mach modular forms, and all of you know that essentially on his deathbed Ramanujan was outlining this new theory in his last letter. But it took mathematicians 80 years to formulate precisely what Ramanujan meant by these functions. And in modern language, the Mach modular forms look like they're extensions of classical modular forms, right? Take your classical modular forms, drop a few holomorphic conditions, and then all of a sudden you get this new world of Mach modular forms, and those are interesting in their own right. Study the Fourier coefficients, expansions, etc., etc. So it's all very neat and tidy, and we're only understanding it now. There's what's called a shadow operator. You take a Mach modular form, you shadow operator moves it back into the world of ordinary modular forms. You can study these ordinary modular forms, and there are nice formulas now that tell you the coefficients of the Mach modular forms are built up out of this holomorphic part and the holomorphic shadow part and the non-holomorphic part. So this very interesting theory has developed. And Mach theta functions, which Ramanujan was talking about, were really Mach modular forms of way to have. And for him, the word theta function was code for modular form. That's the idea. That's the way you should think of it. So Hardy thought all was well until January 12th. He had received his letter describing this new theory, and they're now the subject of current research. And the Brunier-Ono business that I discussed is based on that work. And Freeman Dyson, famous physicist, also a number theory person, mathematician, says that the Mach theta functions give us tantalizing hints of a grand synthesis still to be discovered. It should be possible to build them into a coherent group theoretical structure analogous to the structure of modular forms which Hecke built around the old theta functions of Jacobi. So this remains a challenge for the future. And I think now, 100 years, literally 100 years after Ramanujan's death, we know that there's a new theory of Mach modular forms, and Dyson is right. Now, I want to close with what I find really amazing statement of G.H. Hardy on Ramanujan. I don't know how many people have really read this book, Hardy's 12 Lectures on Ramanujan. I think it's a small book, well worth reading very carefully. And if you read it carefully, especially what Hardy writes about Ramanujan, it kind of brings tears to your eyes. There's a lot of emotional content in that thing. And this is the most striking passage that I found in his lectures. Hardy begins his lecture series saying, I have to help you form some sort of reasoned estimate of the most romantic figure in the recent history of mathematics. Now remember, he's writing this in 1936. 1936. Ramanujan died in 1920, so it's about 16 years after. And he's writing it to an audience that doesn't really know much about Ramanujan's work, and he has to give a survey. It says, real difficulty for me is that Ramanujan was, in a way, my discovery. Now, he's not making an egotistical statement. When he says it's my discovery, he knows what he means by that. He says, I did not invent him. Like other great men, he invented himself. But I was the first really competent person who had a chance to see some of his work. And I can still remember with satisfaction that I could recognize at once what a treasure I had found. So we go back to that, that midnight to 3 a.m. in the morning. He knows a treasure he had found. And my association with him is the one romantic incident in my life. And this is what, to be understood in a metaphorical sense. The romance of mathematics, the romance of collaboration, the romance of excitement. You know, there's, as they say, if you want to enjoy, enjoyment is often multiplied if it's together, in the sense you eat together, you enjoy more, you share mathematical ideas, you enjoy more. To enjoy mathematics, perhaps, you enjoy more through collaboration. The excitement is great. And we can see some of this. If you look at Ramanujan, I mean, look at Hardy's life. Hardy's two great collaborations are with Ramanujan and Littlewood. Both have been very profound and prolific. And so I think Hardy knows exactly what happened in his life, and he's thinking of it as a blessing. So I think it's fitting to leave you with, fitting to leave you with, I'm sorry, this picture was supposed to disappear. Maybe it does. Let's just see. Did I do this? Nope, I didn't do it correctly. Sorry about that. Let me go back to the last slide again. Yeah, this is it. Let's try. I'll read it then, okay? Just slideshow, start from current slide, okay. What's going on here? Okay, I can't seem to work this thing, but I'll read it out to you. On a height he stood that looked towards greater heights, our early approaches to the infinite, our sunrise splendors of a marvelous verge, while lingering yet unseen the glorious sun. What now we see is a shadow of what must come. So this is from Aurobindo, and the slide is not working properly. It says donate. I won't get rid of this one here. I don't know why it's different versions of PowerPoint, I think, have their own quirks. Anyway, this line, this verse is from Savitri, Aurobindo's epic poem of 2 volumes. And I always keep finding new verses that inspire me and are fitting. And it seems that these lines from Aurobindo's work are fitting tribute to Ramanujan and his legacy. Thank you for your attention.
Thank you. Are there any questions?
Others
Yeah.
went through the medical record and sort of guessed that the diagnosis that was done was probably not proper and it was not tuberculosis. And if the proper diagnosis was done and it properly treated, he could have lived more.
Yeah, I think that's right. And also, wasn't it the case that he had some sort of incomplete surgery in Chennai before he went to England, and that also aggravated the problem? Yeah. Yeah, there's a lot more stuff now we know, right? And of course, the letters, we now know about the letters, that they were not being received by his wife. Yeah. Okay.
Sorry, in continuation of Balu's remark, 1917 or 1918 was also the time of Spanish flu, exactly analogous to COVID now. And apparently some 20 million people died in India itself. Even Gandhi was affected by that. And of course it was due to the war situation, and people who took part in the war brought it here. I don't know whether any... Because it seems to be tuberculosis also linked to the lungs.
Yeah.
So I don't know.
Yeah, you're right. You could be.
Could be.
Yes.
Anyhow, that's for mainly historic purposes.
Yeah, it's a good
I just
point.
wanted to ask you about that 1729.
Yeah.
In his notebook, he has written several other things where the sum of 2 cubes being written with a difference of 1 being added. That is, a number is written as sum of 2 cubes in 2 different ways, but the second one is always 1, plus or minus 1. And is there any, because it looks like almost he was trying to write something like Fermat's last theorem up to the addition of 1.
Well, I don't know whether he actually worked on Fermat's last theorem or anything related to that, but certainly he was looking at properties, divisibility properties, numbers, and numbers of these forms, like sums of cubes and sums of, So plus or minus 1 is again minus 1 is also a cube, right? So that would be sum of 3 cubes, with the number 1 being another cube. But I don't know really, and I think there's a continuation of that particular story where Hardy asks him, what's the next number that can be written, or can be so written? And he thinks for a while and says, whatever it is, it's very large, and I think recently somebody worked it out, and it is humongous.
No, it is there in his thing. He has given 3 series.
No, but that the next number that can be written as a sum of 2 cubes in 2 different ways is, I think, in the 200,000, 300,000 level. That's I think somebody worked it out, and I may have even put it in my legacy book, what the example is. Yeah.
Euler already had.
Yeah, Euler had noticed that. Yes.
Any other questions? So if not, let's thank the speaker again. So all of you can gather outside for high tea. Thank you.